So in these next few videos, I'm going to go through lots of examples of evaluating the limits. And when it comes to the actual calculus here, so the process for evaluating the limits, essentially what we'll do is we'll try just plugging in the value with direct substitution and try to simplify. But a lot of the cases that we're going to see here are where if we try to do that, it actually comes out undefined. And with that, we need to bring in all of our skills from algebra and pre-calculus to try to simplify these functions before evaluating. So what I recommend doing is, if you can, try out these problems first. So you'll plug in the value, see if it simplifies. If you get a single number out, awesome, done. But for most of these, what we'll find is that we need to simplify the functions first. So we'll use methods of factoring. Sometimes we'll use a little trigonometry or logarithm properties. Different pieces are going to come through here. So what can be good is to try simplifying the functions yourself first, so that then you can catch any errors that are coming through with algebra that way. But with that, for this video, let's get started with these 4 examples. So this first case is we're plugging in and just taking a look at this function here. We can tell it's a quadratic function. And just kind of what's going on in the background of my mind, quadratics, that's when we graph a parabola. We're not going to run into any issues of plugging in here. So with that, we're just going to plug in -2, and we'll just make sure we do this all correctly and using parentheses. So this is what it looks like with direct substitution. And then with that, we just simplify down. So we're going to have a 12 plus a 10, so 22 plus 4, so a 26. So our limit can be found with just direct substitution, not running into any issues there. With this next example, and this is going to be a rational function, and with that we can run into some issues either with asymptotes or with holes in the graph. So if we try direct substitution here, what's going to happen is we're going to end up being undefined. In the numerator, we'd get 0 out, and also in the denominator, we'd have a 16 minus 28 plus 12 will all turn into 0 there. So that would make it look like that the limit is undefined, but what we need to do is try to simplify this algebraically first. So to do that, with my rational function, what I want to do is factor the numerator and denominator. So we're still evaluating this limit as x approaches 4, and in terms of notation, we want to keep that there until we can actually plug in 4. So up above here, where I have this limit x approaches -2, that would stay as part of the work until we plug in -2, which in this case was in the very first step. So I lose my limit notation because I plugged in -2. With this one, I don't want to plug in 4 yet because then it all falls apart. So for now, I need to keep that limit notation because I'm still evaluating the limit of this function. I just need to simplify that function. So our notation is going to be important here. So try to follow with keeping limit as part of the notation as we go through. Okay, factoring the trinomial in the denominator there, we're going to need an x minus 3 and an x minus 4. And then with that, I can see common factor. So with that, we're still evaluating our limit as x approaches 4, but now I'll have a 1 in the numerator and an x minus 3 in the denominator. And now I can go ahead and plug in 4. So that's going to be equal to 1 over 4 minus 3, which is a 1 over 1. So my limit is going to be 1 for this function. So notice that limit notation stayed there, and then we lost the limit notation in this step because we substituted in that value of 4. All right, with this one, if I try direct substitution, so I'd take the square root of 5 squared minus 5 minus 20, which is actually going to be okay. So something I'd want to be careful of here is if I was trying to take the square root of a negative, but I can just go ahead and evaluate this one. So we'll be taking this big square root, 5 squared minus 5 minus 20 equals square root of 25 minus 5, which is 20. So 20 minus 20 for a square root of 0, which is just equal to 0. So getting a limit out of 0, perfectly fine. It's when our limit goes undefined that we need to be careful. Okay, and this last one, I even included a graph so that we could see what's happening with these cases where it appears undefined, but then we can simplify it. So if we plug in 5 at this point, so actually we just looked at taking the limit of that numerator, so that would give us a 0. And then in the denominator, 5 minus 5, also 0, so now it becomes undefined. So what we want to do is see, can we simplify our function? So we'll use factoring here. So we have this big square root, and we'll have a t minus 5 and a t plus 4. T minus 5. And with that, we have common factors that we can cancel out. So this would be the same as evaluating the limit as t approaches 5 of the square root of t plus 4. And with my graph over here on the right-hand side, when we simplified, what essentially happened was we filled in that dot that's no longer undefined. It's undefined in our original form of the function, but as we simplified, it filled that in. So now we can just plug in and get the coordinate that would have been graphed there if we didn't have the hole as part of the graph. So now we'll plug in 5, so square root of 5 plus 4, which is square root of 9, which is equal to 3, and that would be the value for our limit. So in terms of algebra skills here, if our function appears undefined, want to make sure we factor, see if we can cancel out any like terms. If you have a case where, let's say, we take that but just change it a little bit, so say it was like limit t approaches 5 of the square root of t minus 4, t minus 5, something like that. So where factoring wouldn't help us and canceling out wouldn't help us. So we'd be running into lots of issues with this one. And so if we can't get to a point of direct substitution so that it is defined, then we have to go to our alternative methods of a table or graphing. But for these scenarios that we're looking at in these examples, we want to try to factor, and if we get nice simplification, if we can eventually plug in, then that can get us to the value for our limit.